Welcome back to ECE 442-542. This is the exam number 2 review session. The process I'm not going to really repeat. We've already seen that or gone through that quite a bit, but I'll allow you to bring both sets of tables if you want. And before we get, well, here are the topics that you're responsible for. Homework number 3, Unit 3, which deals with region of convergence, interval of support, inverse Z transforms, those concepts, and homework number 4, which is discrete equivalence. And I had a question after class last time, and I don't think we've ever really gotten to how do we match gains. So let me just quickly go through matching gains. I did that after class, but essentially you want to match the gains at the appropriate frequency. And what's appropriate? Well, it depends on the beginning transfer function, capital H of S. If it's low pass in behavior, then you would be matching gains at DC. And we now know what DC corresponds to in the S domain and the Z domain. If it's a low pass property or transfer function, we have some kind of shape similar to what I've shown here for the magnitude response of the transfer function. We would match H of S value at DC, which is H of S when S is equal to 0. We could calculate that. Then we would set that equal to H of Z when Z is equal to 1, when H of Z has some unknown gain value, K, in it, and you would solve for K to achieve that same DC gain. If, on the other hand, H of S was high pass, then you would let S go off to infinity in H of S, and that will give you some number. And you would now use that number to solve for the unknown gain in your H of Z, and you would use Z equal to minus 1 in your H of Z formula. You could now solve for the gain K in H of Z, and now you have the overall transfer function in your discrete equivalent using pole zero mapping. I wanted to sort of squeeze that in before we get too much further. It keeps being pushed off or out of the time length that we run into, so I sort of rewound the tape and I wanted to play that first in this particular review session. Is that clear? And you could match at any frequency you wanted. If you had some kind of bandpass behavior, you could actually start finding some frequency. That might be at J50. It's 50 in terms of frequency, and you now just say H of J50, and that gives you a value. And you might want to just take the magnitude of that and then match the magnitude of H of Z at that same 50, and hopefully that 50 is consistent with your sampling frequency. But in this class, most of ours will be dealing with low pass and high pass. So you need to be able to, and I might say match at a given frequency or at the best or at a good frequency, and you have to sort of be able to quickly say, oh, this H of S is low pass. Oh, this H of S is high pass. Now I know which frequency to match. That's what I'm expecting you to know for that pole zero mapping strategy for matching the gains. I hope I'm back to the right location. So now let's talk about region of convergence and time interval of support and how you might relate those. And what did I say? Until you graduate, you better remember this formula. Or, I'm sorry, at least until the final exam in this class. You need to know the capital X of Z, the Z transform definition. capital X of z is equal to this infinite sum from minus infinity to infinity of x of n, z to the minus n. So you're weighting these time sequences, these time sequence values, little x of n, by this complex variable z to the minus n. And you can write this all the way out. From minus infinity, you probably don't want to start there, but you might start at something a little less adventurous, like n equal minus 2, n equal minus 1, and then go on up, just to get the idea. Now, based on that, what can you infer, or what can you tell from this information? You can actually tell a lot from just the expansion of this Z-transform definition, this series expansion. I've now highlighted or curly braced a couple of different sections of this series. The blue curly brace corresponds to what time interval in our time domain sequence? This corresponds to n equal minus 1, n equal minus 2, n equal minus 3. We call those the non-causal. And now we can, I'm sorry, I can cut my paper and paste in. I apologize for that. I needed some more space. Uh-oh, here come the tomatoes. But what do we have? It's getting late, so I apologize for being a little crazy, but it's going to have to get us through, right? If you now had a non-causal waveform, what can you infer about its z-plane plot and its region of convergence? Now I would say, okay, I'm one-sided. I'm either causal or non-causal, and I know that one is a disk and one is an unbounded region with the disk removed. So here I would say, oh, what values of z can I tolerate and still have this non-causal section of my series be bounded? So here I have x of minus 2 times z squared, x of minus 1 z. I can't have a really big z. I can't have z going off to infinity, but I can have something shrinking all the way down to 0. Oh, so that might hint you in the direction of saying, oh, your region of convergence looks like this, and my poles are outside of that region of convergence. And that's by looking at a limiting case. If you're okay with that argument, what can you now say about the region of convergence for this red curly brace, which corresponds to the causal? Well, this is just the opposite. If you now plugged in, now you have a constant, x of 0, plus x1 over z, plus x2 over z squared. Well, I can't let z go to 0. I can let z go unbounded. In this case, the region of convergence is outside. And I can play with the different common ratios in these expressions to find the actual value or expression for the region of convergence. But here I would have, let's say, poles that are inside that open area in the z-plane. And what happens when I look at all of these? Now I have a two-sided. And my region of convergence is really this intersection of these two, blue and red, and it has to be a connected region. Which means that, oh, I might have some poles outside of my region of convergence, and I might have some poles inside my region of convergence. I now have this donut or annular for the two-sided. So with the two-sided, I now have this annular region for my region of convergence. And if I had finite sequence, not these infinite sequences, then I might actually have the entire complex plane except maybe for some extremes, the origin or infinity. What happens if I exclude infinity here? In a causal sequence, if I exclude infinity, if I don't let it go unbounded, if I keep it bounded, my region of convergence, what does that allow me to do relative to my terms in the time domain sequence? It switches from causal to what? Something more general. What's more general than causal but includes causal? Right-sided. So now I could come back and do this. Is that making sense? This now I could say is right-sided. What if in this one, and now maybe I picked a poor choice of color, what if I excluded the origin? So here for right-sided, I should say that infinity is not an element of the region of convergence for a right-sided. If I had excluded z equal to 0 in this region of convergence associated with a non-causal, what's a generalization of the non-causal? It's now left-sided. So now I have something that's maybe including those terms. It has a finite number of time domain sequence values that have positive indices. This is now left-sided, which means that 0 is not in the region of convergence. And this is now I've now had a hole punch, a very tiny hole punch, and I've excluded the origin in that disk. And that allows me now to have a more general time domain sequence or a left-sided versus just a non-causal. And this gets even more, how do I want to say this? The region of convergence becomes more extended or more all over the z-plane if you just have a finite number of terms. These are now infinite sequences, right-sided, left-sided, or two-sided. But if I had a finite sequence, I could have the entire complex plane except maybe for the origin or infinity or both. Now, all of that, where the interval of support is all connected with the region of convergence. But does that say anything about whether my waveform in the time domain is bounded or unbounded? Those are disconnected, aren't they? Those are independent pieces of information. Here, then, I could say bounded or unbounded response depends on the modulus of the mode. That's just the magnitude of the mode. How far is that pole away from the origin? That's its modulus. What's the magnitude of that pole? The modulus of mode and the interval of support or the time index window. I'm using some different terms, hoping that some of these might start to resonate. What if we examined non-negative time indices? And suppose that the mode or modes, let's say the biggest mode has a magnitude less than 1. And with non-negative time indices, we know that n is greater than or equal to 0. Does that correspond to a bounded response or an unbounded response? And what you could do is you could go back and you could say, oh, non-negative, I now have this right-hand red region of convergence. My region of convergence is outside all of my poles, and now somebody's told me that the biggest pole is a distance less than 1 from the origin. What does that tell me? It tells me it's bounded, because I could actually say, oh, the unit circle is covered or in that region of convergence. Do you see how to use these pictures and all of these ideas? This now says that I have a bounded response. What if I now kept in the non-negative time indices? I still have a causal, but now my mode, my pole, is further than 1 from the origin in the z-plane. So really I'm saying r to the n is my structure. Here I'm saying r to the n is my structure in the bounded response, and r was less than 1 and n was non-negative. Boom, it's collapsing. Here, r is bigger than 1. And we have an unbounded response. Just plug in a convenient value for r equal to 2. Or you can go back here and you can say, oh, this is my picture. Here's my region of convergence picture. And I've been told that the magnitude of the pole that's bounding that region of convergence is bigger than, let's say, 2, or is 2. Then I know that that gives me an unbounded response. Because 2, 2 squared, 2 to the third, 2 to the fourth, etc. is growing. You can do the same thing for a negative time indices. So the non-negative was causal, the negative is non-causal sequence. N is less, and now let's say that the mode is less than 1. We can slide back up here and say, oh, here's my non-causal region of convergence picture. Now I have an R, one of the poles that's bounding that region of convergence is less than 1. What happens to that mode when I have negative time indices? I have 1/2 to the -1, 1/2 to the -2, 1/2 to the -3. That's now going crazy, isn't it? So this now says that for r less than 1, I have an unbounded response. Contrast that with the mode r being bigger than 1. Now that's good. So now, whether or not you have poles outside the unit circle or inside the unit circle obviously depends on what's my interval of support, or what are my indices where this is defined. Because in this case, for a non-causal sequence, if I have poles that are outside the unit circle, that's a good thing. These now, if I'm interested in a bounded response, this gives me a bounded response. That's how you can now quickly try to decide what's going on with region of convergence, interval of, or time indices, or interval of support, and bounded and unbounded behavior of the waveform. If you're wanting to do an inverse C transform, what's probably the first thing you want to do? Factor or find the roots, right? Or, in this case, if you have polynomials in Z, what do you probably want to make sure is true relationship-wise on the numerator and the denominator? You probably want the numerator, you do want the numerator's polynomial to eventually, when you're Z inverse C transforming, you want the numerator polynomial to be the same or less than the degree of the denominator polynomial. So you want it, and somebody said, do we have to do long division? Because they were going to go spend the next 48 hours learning long division. And I said, focus on what the practice exams are covering. Hopefully it won't take you 48 hours to learn how to long divide, but if it does, spend the rest of the semester learning how to do long division over a length of time, and we'll worry about that in the final. Okay? But in this case, we'll probably have this being proper, meaning the numerator order is the same or less than the denominator, not strictly proper. So proper is when the numerator order is the same as the denominator order, and that's what's okay for y of z. So now if this, let's say this is now z squared plus 2z over z minus 1/2, z minus 1/4. You can inverse Z transform that, right? Because now you're looking at y of z over z, and that's in the right structure that you need. So you'll want to check now or factor the denominator roots. And if they're real, what kind of an structure do you have? Response structure. If you have real roots, real values of z, if they're on the real line, what kind of structure do you have in your time response? Non-sinusoidal. Exponential is the term I was looking for. So now it's non-sinusoidal, non-oscillatory, it's exponential. So now I would say if it's real, we have an exponential. And if it's complex, now we have some oscillation present. And if it's inside the unit circle with a causal behavior, then it's exponentially damped. Suppose we had the following. Suppose I gave you y of z is z over z squared minus 0.75z plus 0.125. And somebody tells you that the region of convergence is the magnitude of z is bigger than 1/2. Can you factor that? Already gave it away, didn't I? Did you see that? So guess, you have 1/8 as your constant, and that's probably what, 1/4 times 1/2, and you have the sum of the two being 3/4. So 1/2 plus 1/4 is 3/4. This now factors into z minus 1/2, z minus 1/4. Or you now have y of z over z is a1 over z minus 1/2 plus a2 over z minus 1/4. And if you find the a1 and the a2, you can do that with the cover-up method. If you want, you'll find that that's 4, 1/2 to the n, minus 4, 1/4 to the n, and it was associated with a causal waveform. Hopefully that's correct. If it's not, you can correct it and you know that I was wrong. That one you should be able to do very easily. What if we had the following? What if we now had y of z equaling z minus 3/4 over z squared minus 0.5z plus 0.625, and now somebody says that the region of convergence is such that, whoops, that the magnitude of z exceeds the square root of 0.625. Or this, if we took the square root, ends up being about 0.8, 0.7906. That actually has complex roots. And we know that the real part doubled is 1/2. So we now know that this is z minus 1/2, whoops, z minus 1/4 squared plus ends up being 3/4 squared. So where are my poles located in the complex z-plane? If I now have it factored as z minus 1/4 squared plus 3/4 squared. Where's my real part of those complex poles? Can you see that, or is it immediately clear from this structure of the factored form? The real part's at 1/4. The imaginary part's at 3/4. I now have 1/4 and J 3/4 for a pole, and the other pole is at minus J 3/4. And if I wanted to, I could actually find this in terms of polar form. I can now find the hypotenuse, and I can find that angle. Or now I have poles at 1/4 plus and minus J 3/4. The magnitude of Z, this is now the hypotenuse. That's R. That's the square root of 1/4 squared plus 3/4 squared. And you could have seen that as R squared is 0.625. So R is the square root of 0.625. But if you do it this way, you end up with this is now the square root of 10/16, which is 0.7906. And what's the angle of this pole, which I called theta sub d? It now has a vertical part of 3/4 and a horizontal part of 1/4, and that ends up being 71.56 degrees. Meaning, if you wanted to, you now have Z is equal to R at an angle of theta sub D, and you could say, oh, Y of Z over Z is now some K1 over Z minus R e to the J theta sub D plus K1 star Z minus R e to the minus J theta sub D. If you wanted to perform it in complex numbers. You could use a table as well if you keep the denominator, or the table probably will have these coefficients as real, and you can now find what your parameters are based on that factored form or that structure of your denominator. I'm showing a different way if you wanted to find it. How would you find K1? Well, you could use, and now it's very important that K1 is associated with the pole at R e to the J theta. It's in the upper half of the Z plane. So now if I use the cover-up method to solve for K1, I would multiply all terms by that factor underneath K1 and evaluate at the value of Z where that factor vanishes. Or I now have Z minus 3/4, which is what is left up here when I look at Y of Z over Z. And the numerator is Z minus 3/4. The denominator is Z minus R e to the minus J theta sub D. That's what's left when I've now canceled that other factor by multiplying through by Z minus R e to the J theta, and I evaluate this. And that becomes some complex number. You can plug in Z equal to that complex number and find what K1 is, and that will be a complex number. So I want Z to be R e to the J theta sub D, and what's underneath is Z minus R e to the minus J theta sub D. So I don't want that denominator to vanish. Hopefully I've multiplied through by the correct factor, and now I come up with a complex number for K1. K1 is some K1 magnitude at some angle of K1. And now I can immediately write down, once I know K1, and that's the only thing in this expression making up y of z, I now have y of z is K1z over z minus. Y of n is now 2 times the magnitude of K1, r to the n. R was the radial distance that pole was away from the origin, cosine of theta sub dn, that's the radians per sample, that's the theta sub d that we had before, plus the angle of K1, and that's for n greater than or equal to 0. Do I need to justify where that comes from? Do we need our 2-year-old hat, or can I move on? Let me put the 2-year-old hat on, just because it takes 3 minutes, and it's 3 minutes that hopefully is well worth it. Justifying where this comes from if y of z is equal to this. K1 is complex. And we know that y of n is equal to K1, what? Pole to the n, z to the n. And the pole, and K1 was associated with the pole upstairs, or in the upper half of the z-plane, r e to the j theta sub d to the n, plus the conjugate of K1, r e to the minus j theta sub d to the n for n greater than or equal to 0. And now we just need to do some algebra with complex numbers, rewriting K1 in the polar form. K1 was the magnitude of K1 at an angle of K1. Its conjugate is just going to be same magnitude with a negative sign. So we have the magnitude of K1, e to the j, and I'm now going to say there is K1 in polar form, or in phasor form. K1 at an angle. The angle is e to the j at an angle of K1. R to the n, e to the j, theta sub dn. That's the first piece. Plus the second piece, K1's magnitude's the same. Its angle is now e to the minus j K1, r to the n, e to the minus j theta sub dn. Are we okay with that step? We're just using the fact that K1 is complex, and we're writing it as magnitude e to the j theta for K1. Now let's combine the complex exponentials, and the same magnitude and r to the n are common to both. So we can collapse this and say magnitude of K1, r to the n, and what's left? Well, now we have e to the j theta sub dn plus angle of K1 plus e to the minus j theta sub dn plus angle of K1. And that should just be screaming at you as far as what that represents. This is 2 times the cosine theta sub dn plus the angle of K1. And that allows us then to say that y of n is in fact 2 times the magnitude of K1, r to the n, cosine of theta sub dn plus the angle of K1. And that's if you've written or found this partial fraction expansion using complex numbers. Just another way, and if you want to use this instead of one of the table entries, maybe this one seems more intuitive. than the table. Let's talk about discrete equivalence. How many main types are there? Is that a loaded question? It's not meant to be. We had zero order hold, discrete equivalence. We had numerical integration, discrete equivalence, and we had pole zero mapping. So we have three main types. And within those, we have different ways of doing them. But here I'm going to say three main types. We have zero order hold, and we can do that using the transform or transfer function approach, which is 1 minus z to the minus 1 z transform of g of s over s. And we have the state space. And I think everyone just gets all warm and fuzzy when we do the state space zero order hold. Yes? So now in this transfer function based zero order hold, I'm absorbing a lot of information into this definite. I've sort of said, here's the wink and a nod way of interpreting the z transform of g of s over s. So if you had to do that manually, you would inverse Laplace transform and then find the z transfer function of each of those individual pieces. But you don't really have to do that. You just have to do a partial fraction expansion of g of s over s and look at that table that compares the S domain row, or on that row it has the Z transform expression with it. So now if you can find one of the pieces inside that curly bracket in the S domain row, you immediately know what its Z transform is. And then you simply have to pre-multiply all of those by Z minus 1 over Z, or 1 minus z to the minus 1. That's why that second table of transforms might be helpful. But in the state space, we have phi is equal to e to the at, and we can find that by hand or numerically, however we want to do it. And what is gamma? Gamma is this integral from 0 to t of e to the a mu. So if we had e to the at, we could find e to the a mu. That gets multiplied by the input matrix in the continuous time, d mu. And this that's really scenario number 2 that we had originally called which of these are we dealing with. This is where the hold is included in the discrete equivalent. The behavior of that hold. Holding the input constant between samples. Question? When we do the zero order hold equivalent, I just gave you the dynamic equations. I gave you phi and gamma. The output equation has an h and a j, but in the zero order hold equivalent, those are the same as c and d in the continuous time. So is that what you were asking? This h is equal to c and j is equal to d. Were you asking about the state space representation or the transform? There's no t, so where is the t? Where's the t? It's hiding. It's hiding in this definition of the z transform of g of s over s. If you wanted to go through all of the steps inside that, you would have to inverse Laplace transform the g of s over s and find some t's, then sample that and get a sequence of numbers and z transform that sequence of numbers. We're embedding all of that or hiding all of that in that expression for the z transform of g of s over s. So I would suggest that by this point we've now grown up enough in our level of understanding that now we don't have to go all through those steps. Let's just find a g of s over s partial fraction expansion, find those individual terms, and start comparing those with their z transform brethren or their pair. Is that okay? So now I'm sort of assuming that we're not going to go through that much detail to find the zero order hold equivalent. We did it a time or two just to see where it comes from or how it works, but at this point let's just quickly match terms in a table and go on. That's scenario number 2. Scenario number 1 had the other two main types. One was numerical integration. And now we could do the transform. That was the substitution table. Or we could do the state space. And that we derived earlier today. That was homework number 4, problem number 5. Or we have, that was one column in the table. So here's our table, and you can refer back to homework 4, problem 5. And the numerical integration had forward, backward, and trapezoid. Or we could do the pole zero mapping, and that one we really were just dealing with the transfer function. And this one, the main difficulty might be the zeros at infinity. How do we handle those? And in this class, our default is map all of the zeros at infinity to these z plus 1 factors. If I say, oh, wait a minute, because of implementation concerns, maybe our input to the filter is not available at the present time, then let's reduce that number of zeros at infinity that are mapped to z plus 1 factors by 1. But I think at this point we aren't going to worry so much about that. Now, we've talked quite a bit, I think, today about the numerical integration and the z-transform. Can I jump ahead and do the pole zero mapping first this time? Because it seems to get shorted every time because we run out of time. And I started this session talking about pole zero mapping. Let's sort of put it in the middle. The key to this is using z is equal to e to the st. And that's true for poles and the finite zeros. What's PZXS? That's the pole zero excess. That's the number of poles minus the number of finite zeros. That gives us the number of infinite zeros. And that tells us how many of these z plus 1 factors we have in our discrete equivalent. Now we have all of the factors, zeros and poles. We just need to find the gain k. And we find that gain k by matching gains between the h of s and the h of z. So what if the gain at DC is bounded? Where do we match the gains? Suppose we have a transfer function, h of s, and somebody says, oh, the gain at DC is bounded. The heck? What does that mean? That just means that you have a finite number for the DC gain. That means if you evaluated this h of s at DC, you'll get a finite number. It won't go crazy on you. It won't go unbounded. If this is the case, where do you match the gains? Match at DC. What does that mean? Well, it means two different things because you have h of s and you have h of z, or you have g of s and you have g of z. G of s is what? Where is DC at g of s? S equals 0. And we set that equal to where is DC for g of z? That's at 1. What if somebody gave you g of s is equal to 1 over s? Is that bounded at, what is that system? What is that system? This is not a signal now. Let's say this is a system. If you said, oh, that's a system, what's it doing in the time domain? What's 1 over s do in the time domain? What's s do in the time domain? A multiplication by s in the frequency domain does what in the time domain? So 1 over s integrates, s differentiates, doesn't it? So this is really an integrator. If this was a system, this is an integrator. What's its gain at DC? Is it bounded? Does this have a bounded gain at DC? What happens if you put in a constant to an integrator? You put in a constant to an integrator, what's the output going to do? Pardon? It's linear. Our integrator is linear, but if I put in 2 to an integrator, and I just kept integrating 2, what happens? I get 2t, don't I? What happens as t goes to infinity? Is it bounded? No. So I can put in a bounded input and get an unbounded output for this integrator. An integrator is not very friendly in terms of control, but it does do some good things in a control setting. It helps shrink errors, but you have to have some feedback around that integrator to make it work. But here, what would you do? If I told you to do a pole zero mapping of this, could you do it? Where's the pole? At the origin. So what's the pole in G of Z? Is that it? Where does 0 in the S-plane map in the Z-plane? It maps to 1. So you should have a factor in the denominator that vanishes when Z is equal to 1. Does that look okay? Now what? Well, we probably need some gain. But how do we pick the gain here? Can't pick DC, can we? We could just pick an arbitrary value. We could say, oh, let's pick a gain at 1 radian per second and match that. So we could say something like, oh, the gain of G of S with S equal to J1, that's now the magnitude of G of J1. That's the magnitude of 1 over J1. What's that magnitude? What's the magnitude of J? If I said plot J in the S-plane, where would you plot it? It'd be on the imaginary axis. How far away from the origin would it be? 1. So the magnitude of J is 1. What's the magnitude of the numerator? What's the magnitude of 1? 1. What's the magnitude of J1? You have 1 divided by 1. 1. So now you know that this is equal to 1, and what do you want to do now? You now have G of Z equaling K over Z minus 1. Yes? Pardon? Why don't I have the Z plus 1 factor in my numerator? That's a good question. Maybe I should. I was just checking to see if you'd laid your head down on your pillow. For this class, what did I say? Probably we default to pole zero excess giving us a Z plus 1 factor. So I should have included it. Good, that's going to help my gain calculation, isn't it? It's going to improve my, well, it wouldn't matter so much, but here let me now say we had a pole zero excess of 1. So let's include, since we have 1, 0 at infinity, let's include this factor Z plus 1. Thank you. Is that better? I'm doing this on the fly if you couldn't tell. Need to kill that fly. Where are we? Trying to match gains. What value of Z do I use? I didn't pick a capital T, did I? So it's going to depend on that capital T a little bit. But here I would say z is equal to e to the st, but what was s? S is equal to j. Can I have any more cascading? I have e to the jt, and I would need to pick t, but we could, but do you see how you would solve for k? You would plug that value of z in here, find the magnitude, and solve for k bar. That was an aside. Let's look at another piece. So that's sort of finding the gain at an arbitrary frequency. What if g of s is such that the gain at dc is 0? That doesn't help us to match, does it? But let's say that the gain at infinity is bounded. Now where do we match gains? And what would maybe give rise to something like this? Well, some magnitude like that. It's going off to 0, isn't it, in absolute sense? So now we want to match at infinity. And we would now have what's z? And we could solve for the k. How much more do we want to talk about? Should I talk about any more on the zero or the pole zero mapping? As far as why we might not want to include a z+1 factor, or can you get that from the notes that I posted for homework hint number 4? Or do you want me to talk about that? No? Yes? Oh, that makes it difficult. Or do you want me to talk about something else? Is it clear how to do it? Yes. What was the question? So what's the difference between a slow pole and a fast pole in the z-plane? So now let's say that I have a z-plane, and let's say here is 1, and I put a blue pole and a red pole. Which of those poles is fast? I have 2 poles. One is faster than the other. Which of these poles? Sorry, I was going back to something else that you never watched, maybe. Which of these poles is fast and which one is slow? They have to be relative to each other. One is faster than the other, and one is slower than the other. How do we determine that? What is fast in the z-plane? Closer to the origin is faster, right? If we were right at the origin, boom, in one step, if we were a first order system, in one step we would be done. We would be right at 0. We would have all of our exponential decrease gone. So this, in this case, that's fast, and that's slow. Which of those poles dominates? So the slow pole is the dominant pole. What does that mean? If I had to calculate the settling time, Which of these poles would you use? So let me say that this is at R1 and this is at R2. Which of those would you use for the settling time? You can't wait for this lecture to speed up, can you? But that's not my question. I'm not asking the mode or the structure of this lecture. That was oscillatory. These are exponential. Which one do you use? Which pole do you use to determine the settling time? R sub 1 or R sub 2? You use the one that's closest to 1, don't you, in magnitude? That's dominating, that's determining your settling time. So T sub S, you want to use R1 dominant or the slowest pole. So now what would happen if I put an R3 out here? Is that what you're asking, sort of?
Yeah.
So now if I have an R3 out there beyond 1, what do I do for settling time? Did you know what that was? That was a punt. Actually, oh, I just pulled. But if you punt, what am I meaning? Well, you don't have a settling time because this is going unbounded. So you can't even talk about a settling time. If this is a causal system, so that's what you need is you're now need to know, is this happening for non-negative indices or negative indices? We're assuming now that it's non-negative indices, it's causal. Then if we had an R3, we couldn't even have a settling time discussion because it's swamping every response that we have. R1 and R2 are just going down to nothing, but R3 is blowing up, and so we've lost all hope, as has this lecture. Yes? So in the S-plane, what are we using? I'm losing audience. Right and left, it doesn't matter which. I think they're in the which plane if they're exiting, if they're going unbounded. In the S-plane, which plane are they in? If they were going unbounded, what plane were they in, right or left? The right. So they have positive powers. Now I've forgotten your question. You said something about a pole here and a pole here. Which one do you use for settling time? Is that true? Which of these poles, black or red, do we use for settling time? Which one's fastest? So if you get confused, what can you do? You can label these. Suppose that we put something here. Let's say this is -2 and this is -4. So now we go, okay, well, I know what these are. This is now e to the -2t for its structure, and here is e to the -4t for its structure. Which of those is fastest? Which one decays quickest? E to the -2t or e to the -4t? E to the -4t. So here this red is fast. This one is slow. which one dominates? Which one do you see the longest? Which one is the slowest? Right? That one dominates. So here's your dominant. And which one do you use for settling time? So here, which one is going to last the longest? That's the one you use for the settling time. So here you would use S equal minus 2 for, whoops, for settling time. So if you wanted, now you would say something like e to the minus 2t, and what's the time constant for this guy? What's the time constant for e to the minus 2t? When is it equal to e? What is the time constant? It's the value of time when this is at e to the minus 1 in magnitude. So now we're saying, oh, when is this time t equal to, or what value of time t makes the exponent minus 1? So now the time constant is 1/2. So we now say 2t is equal to 1, or the time constant is 1/2. And if we had a settling time of 5 time constants, how long would we have to wait before this would be basically gone? After 5 time constants, 5 times 1/2, 2.5 seconds, we basically are finished watching this shake. It's exponentially done in 5 time constants. It's at 1% of where it started in 2.5 seconds. So the settling time, if we were saying a 1%, we're done after 2.5 seconds. Stick a fork in it, we're finished. Did that help? But that's in the S-plane, but it's consistent, better be, with the Z-plane. If you forget, just go Z is equal to e to the st. That tells you a lot. And what points are consistent? S equals 0, Z equal 1. That's our DC in the Z-plane, is at Z equal to 1. In a frequency response, where are we in the Z-plane? We're running around the unit circle, and where do we get? What's as high as we can go? It's bounded, isn't it? It's limited. It's at minus 1. And that's equal to omega sub s over 2, half the sampling frequency. That's the biggest frequency we can distinguish in a discrete time sampled system. Other questions? You're good to go. Where there are office hours before the exam if you want, but that's getting kind of close to exam time, but that's okay. Good luck.